This is quiz number 6 on energy balances. First problem, we had a turbine. So let's draw a little turbine. Coming into the turbine, we had steam. The temperature was 800 Fahrenheit. The pressure was 800 psi, so it comes in at high temperature and high pressure. At that point, you can look up the enthalpy is equal to 1398.7, and that's BTUs per pound. The turbine was producing power. W dot was given as 14,000 horsepower. 14,000 horsepower. We need to get that to BTUs per second. So we'll multiply times 0.707 BTUs per second per horsepower. And that comes out to a power out of 98 BTUs per second. Let's see, coming out of the turbine at low pressure and relatively lower temperature, we had 100 psi, and you were told that the quality was, 100 psi as a saturated vapor. So X equals 1. You look up H is equal to Hg at 100 psi, and that's 1187.5 BTUs per pound. Now, the energy balance on the turbine, N equals out, so M dot Hn equals M dot H out plus Q, indicate Q in red, Q lost from the turbine, get rid of that, Q lost from the turbine, which is what we're trying to find, plus, let's see, work out of the turbine, or Q is equal to M dot times Hn minus H out minus W dot, and M dot was equal to, let's see, 50 pounds per second. Hn minus H out was 1398.7 minus, what was it, 1187.5, and minus the work that we took out, which was 9898, and solve all that, and we get this is equal to 10,000. M dot delta H was 10,560. Calculate that, minus 98, and you'll get the heat loss that must have been leaving the turbine came out to 662 BTUs. See, BTUs per second. Oops. BTUs per second. So that takes care of question 1. Question 2, we took the same steam. See, the same steam, but this time we put it through a valve. So let's put steam in at 800 degrees Fahrenheit and 800 psi. Drop it to the same low pressure, 100 psi. And this time we don't get anything for it. We don't get any work out of the valve. So, and also we're going to assume the valve is adiabatic, no heat loss, and we're going to neglect all changes in kinetic energy. So we'll treat this as a throttling process. So for a throttling process, M dot, well, the energy balance reverts to M dot Hn equals M dot H out. And we already looked up Hn. By the way, the M dots cancel. See, the m dots cancel. So you have Hn equals H out, or an isenthalpic process, throttling process, a valve. And so Hn we had already looked up was 1398.7 equals H out, which is, now we're at 100 psi, and if you'll find that that's a superheated vapor. So you go to your superheated tables and you have to interpolate. The interpolation is between 700 degrees and 800 degrees, so T minus 700 divided by 800 minus 700, here's my interpolation, is equal to the H associated with that T, 1398.7, minus the H at 100, see the H at 700 degrees, which is 1379.5, divided by, see, 1429.8 minus 1379.5. Should be able to interpolate that fairly quickly, and when you do, it comes out to a T between 700 and 800 of 738 degrees Fahrenheit. So that takes care of question number 2. Question number 3, we had a compressor. This time we'll draw the compressor with the ideal gas going into it at, and we really don't need to know the pressure, but it was at 1 atmosphere and 80. At this point we don't need to know the pressure, but let's put it down there anyway. Comes out at higher pressure, and let's see, we're trying to find the temperature out. It was told to be adiabatic, so the energy balance is N equals out. We're assuming steady state, so N is m dot Hn plus the work that we put into the compressor. Let's see, there was some work coming in, and that was 300 horsepower. Now 300 horsepower, multiply that times 0.707 BTUs per second per horsepower, and that comes out to, oh gosh, 212, approximately 212 BTUs per second that we're putting into that thing. So m dot Hn plus W dot work in is equal to m dot H out, or W dot equals m dot and H out minus Hn, and for an ideal gas that'll be Cp T out minus T in, assuming our Cp represents that range of temperatures. So m dot, and that equals to 212. M dot was 2, Cp was 0.2, T out we're looking for, and T in was 80 degrees Fahrenheit. Solve that equation for T out, and we get T out is approximately equal to 610 degrees Fahrenheit. So there's 3 fairly straightforward problems on application of the energy balance to open systems where we have steady state, no holdup of energy, no accumulation of energy in the system.